Hey, how you doing? Hope you're having a good day. Today I'm going to do part 2 of my stimulated Raman scattering series. And I'm doing all this based off what I learned in this paper here called Stimulated Raman Scattering from Bulk to Nano. And the authors are Richard Prince, Rene Frontiera, and Eric Potma. So this is my source where I'm getting this information. And I might use some figures and stuff to help illustrate what's going on from this paper. Okay, so let's get into it. So, part 2 is going to be about the development of stimulated Raman scattering. So, lasers were developed in around the 1960s, and they worked off stimulated emission. And it was noticed that sometimes the output wavelength of the lasers, there was actually two wavelengths. There was one wavelength at, say, lambda 1, another wavelength at lambda 2, and the energy difference between the two wavelengths, it was found out corresponded to vibrational energies. So that told them what was going on here. The gain medium inside the laser was Raman shifting the fundamental wavelength that they were trying to produce, and that was producing a second wavelength. So here's what I'm talking about. If we draw our laser, so we're thinking about a laser here. Let's just think about a box. And here's the back. And in a laser, there's two mirrors, one slightly transparent, one completely reflective. So there's our laser, right? And this is a mirror right here. Say this is slightly transparent in that hole right there. So that's where the light is coming out of. And this back mirror is completely reflective. And so in a laser, you have your gain medium, which I'll just symbolize by a star to sort of symbolize that it's electronically excited. And you can make it electronically excited multiple different ways by either a different laser, but if you keep using lasers to excite the gain medium of another laser, well, you got to start somewhere. You could do electrical discharge. There's other ways too. So we'll just call this arrow the source to excite gain medium. So we excite the gain medium, and the gain medium is emitting a photon. I'm not going to draw it as a wavy arrow. I'm just going to draw a straight arrow. Else this box is going to become messy. So it's emitting, we'll call it omega F for the fundamental frequency output. And then there's more molecules inside the laser. Well, more gain medium. And the fundamental is bouncing back and forth off these mirrors. So once the fundamental hits another gain medium molecule, you're going to get two omega F's out because, well, stimulated emission. Okay, and one of these omega F's, they're going to hit this thing, and this thing is going to be our Raman shifter. So it's going to have a relatively strong Raman cross-section. So omega F is going to hit this, and it's going to shift the frequency of omega F down to, we'll call it omega S for scattered frequency. And so that's just spontaneous Raman, could be. But now that we have omega S, we could bring in omega F to this Raman shifter and omega S and we can, well, now this is going to be stimulated Raman right here, because we have our scattered wavelength going in, and we have, this is the wavelength that's going to be shifted to the new omega s. So 2 omega s comes out. Sorry, I drew that kind of close together. These two arrows are omega s. And then, so our gain medium outputs omega f here, but our Raman scatterer outputs omega s. And in that way, in early lasers, they were getting 2 output wavelengths. So, there was an early application of that, namely that you put in whatever Raman shifter you want, and you can sort of tune the wavelength of the laser. And if you didn't want omega f, well, then put more Raman scatterers in there so you only get omega s. If you wanted a different omega s, put a different Raman scatterer in there. But you do have to stick within the vibrational frequencies of the Raman shifters. Okay. So that was going on in the early days of lasers. Stimulated Raman scattering, the development of it followed the development of lasers, mainly because they have the stimulated part in common. Okay, now what else can you do with this scattered light? Well, the stimulated Raman scattered light is coherent just like omega f is coherent. So there's a few properties of lasers that make them nice. One is that the beam is very narrow and it has a very small angle of a divergence. So there's a bunch of light rays coming out of here, right? But they're slowly going to diverge, but only by a very, very small angle. So this angle here, theta, is very small. Whereas with, I don't know, a fluorescent light, if this is just a fluorescent tube, well, it's emitting light everywhere. So, what's the word I'm looking for? The divergence of the beam is not very much, whereas the divergence of a fluorescent light is a whole lot. Now also, the light's coherent, which means that all the waves are in phase with each other. So if we were to draw out the wavelength, it might look like this. Right? So all the peaks meet at the same time, all the valleys meet at the same time. That is coherent light. That's what's coming out of the laser. Whereas with the fluorescent light, it might just be outputting one wavelength, but the wavelengths, one of them might look like that, but the phase is shifted, so therefore it's not coherent. And then you would have a peak in this valley, and you'd have a valley in the peak, just like that. So these two waves are not coherent. These two waves are coherent. So coherent just means in phase. So what can you do with this coherent light? Well, when you vibrationally excite a molecule, so just think of two balls attached with a spring, and they're vibrating back and forth. Think of a few different ones. Right? So you bring light in here, a coherent light. You bring coherent light in here, and then all of these oscillators are going to start oscillating in phase. And all these oscillations are going to be coherent with each other. But slowly, over time, they're going to start to lose phase with each other because of collisions. Right? Some oscillators might bump into another oscillator, which will sort of shift the phase of it. So eventually, they're all in phase like this. The wave I'm drawing here is the bond displacement. Right? This would be bond displacement, this axis. This would be time for the wave I'm drawing here. So that's at time 1. But at time 2, they're going to slowly dephase. First wave might look like that still, but then the second wave is going to look, it's going to be shifted a little bit. So something like that. Still going to have the same wavelength though. The other one might be like this. And now, so all these molecules, we say they're dephased. So what you can do with stimulated Raman scattering, and this was figured out early, was that you can study dephasing dynamics. But it actually didn't come possible to do until they had picosecond pulsed lasers. And that's because these vibrations are happening so fast that, well, you need a very fast pulse, a very fast laser pulse, to see what's going on this time scale. So Raman peaks, if you imagine a peak, it's got a certain full width at half max. And if you take the Fourier transform of the full width half max, you get the lifetime of that vibration. And if you want to know about the dephasing dynamics, your pulse has to be, we'll call the lifetime tau. We'll call the pulse of our laser delta t. So the pulse of the laser delta t has to be less than the lifetime of what you're studying to actually study anything about it. So only with the advent of picosecond pulse lasers did studying dephasing dynamics become a thing. Vibrational dephasing dynamics. And you can also study electron dynamics. So if you have a couple molecules, they have, in this one, you have an electron here, but if it gets excited, it can transfer the electron over here. But that takes a certain amount of time, and that's what I mean by electron dynamics. That's just one example, is charge transfer. And with the advent of femtosecond lasers, electron dynamics were able to be studied, because charge transfer, I actually don't know if charge transfer happens on the order of femtoseconds. But electron dynamics in general became possible with the advent of femtosecond lasers. And with that came a technique called fizzers. And fizzers it's an acronym for femtosecond stimulated Raman scattering. Fizzers. Okay. So what you could do with fizzers is, let's draw two potential energy wells. Let's see, this is the ground state, and this is the excited state. Let's call this S1, S0. You have vibrational states in here. You have them down here. Right? This is your energy axis. This is your reaction coordinate. So what you could do with fizzers is bring in an excitation pulse, so you could excite an electron from here to here, and you would end up in some vibrationally excited state. And then by studying the vibrational dynamics, you can see how the electron decays back to the ground state. Because eventually, well, either these two potential energy surface might cross, or another potential energy surface might cross with this one, but then it could cross again. Eventually the electron could, come over here. Well, the energy would have to be that high for it to go over here. Then it falls down that well, and then would have to cross this somewhere, but it could fall back down here. And so with this fizzers, one thing you can do is map potential energy surfaces. That's what I'm getting at, even though I got these ugly ass drawings. Okay, so that's a little bit on the development of stimulated Raman scattering. In the next part, I'm going to go over some experimental and theoretical aspects of stimulated Raman scattering. Thanks for watching. Have a great day.